In this lesson, we're going to look at the proof of Rolle's theorem. So remember the statement of Rolle's theorem. It says that if f of x is continuous on an interval ab, differentiable on the open interval ab, and f of a equals f of b, then there is a number c in the open interval from a to b in which f prime of c is equal to 0. So we want to prove this theorem. So we will assume that the conditions hold. We'll assume f of x is continuous, it is differentiable, and f of a equals f of b. And then we want to prove that, or show that, there is a number c between a and b in which f prime of c is equal to 0. Alright, now we have two cases that we're going to consider here. The first case is where f of x is just a constant function. So if f of x equals f of a, which is equal to f of b because that's given, for all x between b and a, well then f of x is constant, and so then f prime of x will equal 0 for all x between a and b, right? Because the derivative of a constant function is equal to 0. In other words, just to justify this, d dx of f of x would be d dx of f of a, which is equal to 0 because this is a constant number right here. And so therefore c could be chosen to be any number between a and b. C can be any value in the interval from a to b. Like that. Alright, so that's the easy case. That's when f of x is just constant. In other words, in this case, its graph would look just like this. If this is a and this is b, we did this case right here where the graph is constant, or where the graph is a horizontal line. Now let's take a look at this case. So case 2, suppose f of x is not constant. Now, before we start this case, if f of x is not constant, there are three sub-cases that can hold. The graph of f could look like one of these cases. So the graph of f could go like this. If this is a and b, the graph of f could go like this, where we have a single maximum value like that, and our minimum value for f occurs at the endpoints. So we have a maximum value for f, and the minimum value occurs at the endpoints. We could also have a case like this, where the maximum value for f occurs at the endpoints, and we have a minimum value somewhere in between a and b. We might have multiple minimum values between a and b, but we have at least one. And then we could have a case like this, where our function might do something like this. So here we have a maximum value occurring between a and b, and a minimum value occurring between a and b, and the endpoints, f of x has neither a minimum nor a maximum value at the endpoints. Now we're just going to consider one of these cases. We're just going to consider this case right here, where we have a maximum value in between a and b. And that actually would be similar to this case right here, where we consider that maximum right there. the other case can be proven in exactly the same way, as you'll see. So what we're going to assume now we'll assume C, the number C, is going to be in between B and A, is where f of x has a maximum value. So we're going to assume that that's where f of x has a maximum value. And now we're going to show f prime of c must be equal to 0. Well, we know that f prime of c exists because we assumed f of x was differentiable. So we know f prime of c exists. So we know, or we're given, that f prime of c exists. Now let's look at the limit definition for the derivative then. So f prime of c would be the limit as x approaches c, f of x that's one version of our limit definition for the derivative. Now let's look at the left and right hand limits for this. If we consider the limit from the left of that quantity, now as x approaches c from the left, the denominator down here, that is always going to be less than 0, negative. The numerator, because f of c is a maximum for the function, you're going to be evaluating a smaller number minus a larger number, so this will be less than or equal to 0 in the numerator. So what we have then is that this limit must be greater than or equal to 0, because you have a negative number divided by a negative number, that's going to be a positive number. Well, it might equal 0 as well if the numerator is equal to 0. Okay, so we have that result. Also note this: if we look at the right hand limit, well, in this case now, as x approaches c from the right, the denominator is going to be bigger than 0 because x is going to be larger than c. So the denominator is positive. The numerator, however, is still going to be less than or equal to 0 because f of c is a maximum for the function. And so this quantity will be less than or equal to 0 because you're going to be taking a number that's negative divided by a positive, that's going to be negative. And, well, it might also equal 0 if the numerator is equal to 0. So, now, if the full limit exists, that means that the left and right hand limits must exist, that these two quantities right here these two values must exist and be equal. Well, if one of them is bigger than or equal to 0, and the other one is less than or equal to 0, the only way both of these can exist and be equal to each other is if they're equal to 0. So therefore, for the left and right hand limits to exist and be equal, so let's say this, so therefore for limit, I'll just use shorthand notation, as x approaches c from the left to equal limit as x approaches c from the right, for this to be true, they both must equal 0. And therefore, f prime of c is equal to 0, because that's the full limit. And we know the full limit exists. And there we go. That's our proof of Rolle's theorem.